Imagine a universe where even your wildest dreams of speed hit an unbreakable wall. Not your spaceship, not your thoughts, not even gravity itself can outrun the ultimate cosmic speed limit, the speed of light. At nearly 300,000 kilometers per second, this isn't just a number, it's the very code that writes the laws of reality. But why does the universe enforce this limit? What cosmic secrets are hidden behind it? And what would happen if we could shatter this barrier? If you're fascinated by the deepest mysteries of the cosmos and want to explore the universe's most mind-bending concepts, make sure to subscribe to this channel and give this video a thumbs up. And one quick question: if you could have a conversation with your future self from 1,000 years ahead, what's the first thing you'd ask? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. To understand why nothing can exceed the speed of light, we first need to grasp what light actually is and why it's so special. Light isn't just illumination from your lamp or the sun's rays warming your face, it's electromagnetic radiation, a self-propagating wave of electric and magnetic fields dancing through space. But here's where it gets strange. Light doesn't need a medium to travel through. Unlike sound waves that require air or water, light races through the vacuum of space at its maximum velocity, never slowing down, never speeding up in empty space. This constancy of light speed was one of the great mysteries that puzzled physicists in the late 1800s. Scientists assumed light must travel through something they called the luminiferous aether, an invisible substance filling all of space. But in 1887, Albert Michelson and Edward Morley conducted an experiment that shattered this idea. They tried to detect Earth's motion through this supposed ether by measuring light speed in different directions. The result? Light traveled at exactly the same speed, regardless of Earth's motion. No ether. No variation, just that constant, unwavering speed. This discovery set the stage for Albert Einstein's special theory of relativity in 1905. Einstein made a radical proposal. The speed of light in a vacuum is the same for all observers, regardless of their motion. This simple statement has mind-bending consequences. It means that space and time themselves must bend and stretch to keep light's speed constant. If you're traveling at half the speed of light and shine a flashlight forward, that light doesn't travel at 1.5 times light speed. It still moves at exactly light speed relative to you and to someone standing still. But why is there a speed limit at all? The answer lies in the very fabric of space-time. You see, we don't live in a universe with 3 dimensions of space and 1 of time existing separately. We inhabit a 4-dimensional space-time where space and time are interwoven. Everything, you, me, planets, stars, is always moving through space-time at the speed of light. Yes, you read that correctly. Right now, sitting still, you're moving through space-time at light speed. Here's the key insight. This motion is divided between movement through space and movement through time. When you're stationary in space, all your motion is through time. You're traveling through time at maximum speed. But when you start moving through space, some of that motion gets diverted. The faster you move through space, the slower you move through time. At the speed of light, all your motion would be through space with none left for time. Time would stop completely for you. This is why massive objects can never reach light speed. As you accelerate, you need more and more energy to increase your speed. The closer you get to light speed, the more your mass effectively increases from the perspective of an outside observer. To actually reach light speed, you'd need infinite energy, which is impossible. The universe has built-in protection against breaking this limit. But photons, particles of light, are different. They have no mass, so they must travel at light speed. They can't go slower or faster. They exist only at this cosmic maximum. From a photon's perspective, if such a thing could exist, Its journey from emission to absorption takes no time at all. A photon emitted from a star millions of light-years away experiences its entire journey instantaneously, even though we observe it taking millions of years to reach us. The speed of light isn't just about light, it's the speed of causality itself. It's the maximum rate at which cause and effect can propagate through the universe. When the sun suddenly disappeared, hypothetically, Earth wouldn't immediately fly off into space. We'd continue orbiting normally for about 8 minutes, the time it takes light to travel from the sun to Earth. Only then would we see the sun vanish and feel the loss of its gravitational pull. Gravity itself propagates at light speed. This cosmic speed limit shapes the entire structure of our universe. It determines the size of atoms, the energy of chemical bonds, the luminosity of stars, and even the possible complexity of life. If light speed were different, the fundamental forces would have different strengths. Chemistry would work differently. Stars might not shine, or they might burn out too quickly for planets to form. The specific value of light speed is woven into the very possibility of our existence. Recent discoveries have only deepened the mystery. The LIGO and Virgo gravitational wave detectors have confirmed that gravitational waves, ripples in space-time itself, travel at precisely the speed of light. When two neutron stars collided 130 million light-years away in 2017, both the gravitational waves and the light from the event reached Earth, having traveled at the same cosmic speed limit across the vast expanse of space. The implications of this cosmic speed limit extend far beyond abstract physics. They shape everything we observe in the universe. Take the simple act of looking at the night sky. When you gaze at the stars, you're not seeing them as they are now, but as they were years, centuries, or even millions of years ago. The beautiful red star Betelgeuse in Orion, you're seeing it as it was about 650 years ago. For all we know, it might have already exploded into a supernova, but we won't know for centuries to come. The universe's speed limit turns every telescope into a time machine. This finite speed of light creates what astronomers call the observable universe, a sphere around us about 93 billion light-years in diameter. Wait, you might think, if the universe is only 13.8 billion years old, shouldn't the observable universe be 27.6 billion light-years across? This is where things get truly mind-bending. Space itself is expanding, and it can expand faster than light because space isn't a thing moving through space, it's the fabric of space itself stretching. Distant galaxies can recede from us faster than light speed, not because they're moving through space that fast, but because space itself is expanding between us and them. The James Webb Space Telescope, launched in 2021, is pushing the boundaries of how far back in time we can see. It's detecting galaxies that formed just a few 100 million years after the Big Bang, their light having traveled for over 13 billion years to reach us. These ancient photons have been racing through space since before Earth existed, before our sun formed, before most of the atoms in your body were forged in stellar furnaces. Every discovery from Webb is a message from the deep past, delivered at the universe's maximum postal speed. But here's something that might blow your mind. While nothing can travel faster than light through space, space itself has no such restriction. During cosmic inflation, a period of exponential expansion in the universe's first fraction of a second, space expanded so rapidly that regions of the universe became causally disconnected. Parts of the universe moved apart so fast that light from one region still hasn't had time to reach the other, even after 13.8 billion years. This is why cosmologists talk about the cosmic horizon, a boundary beyond which we cannot see, not because our telescopes aren't powerful enough, but because light itself hasn't had time to reach us. Let's talk about what happens when massive objects approach light speed. According to Einstein's equations, strange things occur. time dilation becomes extreme. A clock moving at 99.9% of light speed would tick about 22 times slower than a stationary clock. Length contraction squeezes objects in their direction of motion. At 99.9% of light speed, a meter stick would appear to be only about 4.5 centimeters long to a stationary observer. These aren't just theoretical predictions. We see these effects every day in particle accelerators. At CERN's Large Hadron Collider, protons are accelerated to 99.99999% of light speed. At these velocities, the protons experience such extreme time dilation that from their perspective, the 27-kilometer ring appears to be only about 2 meters in circumference. Unstable particles that would normally decay in nanoseconds survive much longer when moving at these speeds, their internal clocks slowed by their motion through space. The cosmic speed limit also explains one of astronomy's most beautiful phenomena, Cherenkov radiation. When charged particles travel through a medium like water faster than light travels in that medium, remember, light slows down in materials, but particles can exceed this reduced speed. They create a blue glow, the optical equivalent of a sonic boom. This ethereal blue light is what gives nuclear reactors their characteristic glow and helps scientists detect high-energy particles from space in experiments like IceCube at the South Pole. But what about quantum entanglement? Doesn't spooky action at a distance, as Einstein called it, violate the speed of light? When two particles are entangled, measuring one instantly affects the other, regardless of the distance between them. Scientists have confirmed this phenomenon across distances of thousands of kilometers. However, this doesn't actually violate relativity. While the correlation between entangled particles is instantaneous, no information can be transmitted faster than light using entanglement alone. The universe seems to have built-in safeguards against faster-than-light communication. The search for violations of this cosmic speed limit has been one of the most rigorous in all of physics. In 2011, the Opera experiment initially reported neutrinos traveling faster than light, sending shockwaves through the physics community. But careful reanalysis revealed a loose fiber optic cable had caused a timing error. When corrected, the neutrinos were traveling at precisely the expected speed, just below light speed, as massive particles should. Modern experiments have pushed the precision of these measurements to extraordinary levels. The Fermi Gamma Ray Space Telescope has observed gamma rays that have traveled billions of light years, arriving within fractions of a second of each other, despite having vastly different energies. If the speed of light varied with energy, these photons would have arrived at different times. The fact that they arrived together confirms that light speed is truly constant to at least 1 part in 100 million billion. The relationship between light speed and gravity reveals one of the deepest mysteries in physics. Gravity, like light, propagates at exactly 300,000 kilometers per second. This isn't a coincidence, it's a fundamental feature of how space-time works. When massive objects accelerate, they create gravitational waves that ripple outward at light speed, carrying information about the changing gravitational field across the cosmos. Speaking of gravity and light, this brings up a fascinating paradox that puzzles many people. If light can't escape from a black hole, how does gravity get out? This is such a profound question that I've created an entire video exploring this mind-bending concept. Check out my video called "If Light Can't Escape a Black Hole, How Can Gravity?" The answer will completely change how you think about gravity itself. The video is in the description and on the card above. The cosmic speed limit affects not just how fast things can move, but the very nature of simultaneity. In Newton's universe, everyone would agree on what now means across the cosmos. But Einstein showed us that simultaneity is relative. Events that appear simultaneous to one observer might occur at different times for another observer moving at a different velocity. There is no universal now that extends throughout the universe. The speed of light limit fractures time into countless individual perspectives. This has profound implications for our dreams of interstellar travel. The nearest star system, Proxima Centauri, is about 4.2 light-years away. Even traveling at 99% of light speed, a journey there would take over 4 years from Earth's perspective. But here's where relativity offers a glimmer of hope. For the travelers aboard the spacecraft, time dilation would make the journey feel much shorter. At 99.9% of light speed, the subjective travel time would be only about 2 months. Push that to 99.999%, and the journey would feel like just a few days. But this creates what physicists call the twin paradox. If you traveled to a star 20 light-years away at near light speed, you might age only a year during the round trip, while 40 years would pass on Earth. You'd return to find your twin sibling, your friends, everyone you knew, aged decades while you barely aged at all. The universe's speed limit doesn't just restrict how fast we can travel, it potentially separates us from our own timeline. Recent observations from the Event Horizon Telescope have given us unprecedented views of how light behaves near the ultimate cosmic speed traps, black holes. The famous image of the black hole in galaxy M87 shows a glowing ring of light, photons caught in orbit around the black hole, traveling at light speed but unable to escape the extreme curvature of space-time. Some of these photons have been circling for thousands of years, prisoners of gravity racing at maximum cosmic speed, but going nowhere. The cosmic speed limit also determines the scale of the universe's largest structures. Galaxy clusters, the biggest gravitationally bound objects in the universe, can only grow so large because gravity can only reach so far in the time available since the Big Bang. If light speed were infinite, the entire universe might have collapsed into one enormous structure. Instead, we see a cosmic web of filaments and voids, shaped by the finite speed at which gravity can pull matter together. Let's dive into something truly fascinating. The vacuum of space itself might determine the speed of light. According to quantum field theory, empty space isn't empty at all. It's seething with virtual particles that pop into existence and annihilate in timescales too brief to measure directly. These quantum fluctuations give the vacuum properties similar to a medium with what physicists call vacuum permittivity and permeability. Light speed emerges from these properties, just as sound speed emerges from the density and elasticity of air. Some theoretical physicists have proposed that in the early universe, when conditions were drastically different, the speed of light might have been different too. João Magejo and Andreas Albrecht suggested that light might have traveled faster in the universe's first moments, potentially solving several cosmological puzzles like the horizon problem, why regions of the universe too far apart to have ever communicated have the same temperature. While this remains highly speculative, it illustrates how the speed of light might not be as fundamental as we think, but rather an emergent property of space-time itself. The Planck satellite, which mapped the cosmic microwave background radiation with unprecedented precision, has searched for evidence of variations in fundamental constants, including the speed of light. So far, the results show remarkable constancy. If light speed has changed over cosmic time, it's by less than 1 part in 10 billion. The universe seems to have locked in its speed limit very early and stuck with it ever since. But what about tachyons, hypothetical particles that always travel faster than light? If they existed, they would experience time backward and could theoretically carry information into the past, creating causality paradoxes. Despite decades of searching, no evidence for tachyons has ever been found. the universe seems to strictly enforce its speed limit, preventing the kind of time travel paradoxes that would make cause and effect meaningless. The development of optical atomic clocks has pushed our ability to measure time to extraordinary precision. These clocks are so accurate they would lose less than 1 second over the age of the universe. Using these clocks, scientists have confirmed time dilation from speeds as low as 10 meters per second and gravitational time dilation from height differences of just 30 centimeters. The universe's speed limit isn't just theoretical, its effects are measurable in everyday situations. The consequences of the cosmic speed limit ripple through every aspect of our existence, from the subatomic to the galactic scale. Consider the fine structure constant, a fundamental number that determines the strength of electromagnetic interactions. This dimensionless constant, approximately 1/137, depends on the speed of light, Planck's constant, and the electron charge. If light speed were different, atoms would have different sizes, chemical bonds would have different strengths, and the entire periodic table would be reorganized. Carbon, the backbone of life as we know it, might not even form stable bonds. The specific value of light speed is literally written into the chemistry of life itself. Modern particle physics has revealed another layer to this cosmic speed limit story. The Higgs field, which permeates all of space and gives particles their mass, creates a fundamental distinction between massive and massless particles. Massless particles, like photons and gravitons, must travel at light speed. They have no other option. They can't slow down or speed up. They exist only at the cosmic maximum. Massive particles, from electrons to entire galaxies, can never reach this speed because the Higgs field creates a kind of cosmic molasses that prevents them from achieving light speed. The universe has essentially created two classes of citizens, those condemned to always travel at light speed and those forbidden from ever reaching it. The Large Hadron Collider has given us unprecedented insights into what happens when we push massive particles close to the speed limit. When protons collide at 99.99999% of light speed, the kinetic energy is so enormous that it converts into mass through Einstein's E equals mc squared, creating showers of exotic particles that existed naturally only in the first microseconds after the Big Bang. We're literally recreating the conditions of the infant universe, all because of the energy concentrated by approaching the cosmic speed limit. But here's something that challenges our everyday intuition. The speed of light isn't about light at all. It's about the geometry of space-time. In regions of curved space-time, like near massive objects, the effective speed of light can appear different to distant observers. Near a black hole's event horizon, time dilation becomes so extreme that light appears to slow down and freeze at the horizon from an outside perspective. Yet locally, light always travels at the same speed. This reveals that the cosmic speed limit is more fundamental than light itself. It's the maximum rate at which space-time allows information to propagate. Recent discoveries in cosmology have added new dimensions to our understanding of this limit. Dark energy, the mysterious force causing the universe's expansion to accelerate, doesn't violate the speed of light even though it causes galaxies to recede from each other faster than light speed. This is because dark energy doesn't move things through space, it creates more space between things. It's like the universe found a loophole in its own speed limit, allowing for faster-than-light recession velocities without actually breaking the fundamental rule that nothing can travel through space faster than light. The cosmic speed limit also plays a crucial role in one of the biggest mysteries in physics, the information paradox of black holes. When matter falls into a black hole, the information about its quantum state seems to be destroyed, violating a fundamental principle of quantum mechanics. Stephen Hawking spent decades wrestling with this paradox, eventually proposing that information might be preserved on the black hole's event horizon. But here's the catch. For information to escape from near the horizon, it must respect the speed of light limit, which means black holes can only release information incredibly slowly through Hawking radiation, a process that would take longer than the current age of the universe for stellar mass black holes. Let's explore what the universe might look like if the speed of light were different. If it were infinite, causality would be instantaneous across the entire cosmos. Every gravitational interaction would be felt immediately everywhere. The night sky would be blindingly bright as light from every star in the universe reached us instantly. There would be no cosmic horizon, no limit to how far we could see. But such a universe would likely be unstable. Infinite forces acting instantaneously could tear everything apart or collapse it altogether in an instant. If light speed were much slower, say only 1,000 kilometers per second, the universe would be a profoundly different place. Stars would need to be much smaller to remain stable. Atoms would be larger and more fragile. Chemical reactions would proceed differently. The observable universe would be tiny. We might only see our own galaxy. Space travel would be effectively impossible, as even reaching the moon would take hours for light and much longer for any spacecraft. Life, if it could exist at all, would be confined to single planets, with no hope of ever exploring or communicating across cosmic distances. The discovery of fast radio bursts, intense pulses of radio waves from distant galaxies, has provided new tests of the cosmic speed limit. These bursts travel billions of light-years to reach us, and their different frequencies arrive within milliseconds of each other. If the speed of light varied with frequency, even slightly, these signals would be spread out over much longer times. The fact that they arrive together confirms that all electromagnetic radiation, regardless of wavelength or energy, travels at the same cosmic speed limit. The Breakthrough Starshot project, proposed by physicist Yuri Milner and supported by Stephen Hawking, aims to send tiny spacecraft to Proxima Centauri using powerful laser propulsion. The goal is to accelerate gram-sized probes to 20% of light speed, allowing them to reach our nearest stellar neighbor in just 20 years. But even this ambitious project must respect the cosmic speed limit. The enormous energies required to reach even a fraction of light speed make it one of the most challenging engineering problems humanity has ever contemplated. Quantum mechanics adds another layer of complexity to the speed limit story. The uncertainty principle tells us that we can never know both the position and velocity of a particle with perfect precision. As particles approach light speed, this uncertainty becomes extreme. The very act of trying to measure something moving near light speed fundamentally disturbs it. The universe seems to protect its speed limit not just through the impossibility of infinite energy, but through the fundamental fuzziness of quantum mechanics itself. The study of cosmic rays, high-energy particles from space, has revealed what happens when particles with enormous energies slam into Earth's atmosphere. Some cosmic rays have energies so high that a single proton carries as much energy as a professionally pitched baseball. Yet even these incredibly energetic particles still travel just below light speed. The universe seems to have an absolute prohibition on exceeding this limit, no matter how much energy is involved. The philosophical implications of the cosmic speed limit extend far beyond physics into the realm of human existence and our place in the universe. This universal constant creates what physicists call the light cone, a geometric representation of all possible paths through spacetime that an object can take. Your past light cone contains all events that could have influenced you, while your future light cone contains all events you could potentially influence. Everything outside these cones is causally disconnected from you. existing in what physicists call elsewhere, regions of space-time that you can never affect and that can never affect you. The speed of light literally defines the boundaries of your potential existence. This concept has profound implications for free will and determinism. Because information cannot travel faster than light, there's always a delay between cause and effect. This delay creates pockets of independence throughout the universe, regions where events unfold without immediate influence from distant causes. In a universe without a speed limit, everything would be instantaneously connected, potentially creating a deterministic cosmos where every event is immediately influenced by every other event. The cosmic speed limit might be what gives us the breathing room for choice and uncertainty. Recent observations from the Atacama Large Millimeter Array in Chile have revealed how the speed of light affects the formation of planets and solar systems. When a star forms, it takes time for its radiation to push away the surrounding gas and dust. This delay, caused by light's finite speed, creates a window of opportunity for planets to form before the stellar wind clears everything away. If light traveled faster, young stars might clear their neighborhoods too quickly for planets to coalesce. Earth itself might never have formed if the cosmic speed limit were different. The speed of light also determines the maximum size of stable structures in the universe. Galaxies can only grow so large before the light speed limit on gravitational communication causes them to become unstable. Galaxy clusters are near this maximum size. Any larger, and different parts couldn't communicate quickly enough to maintain gravitational cohesion. The cosmic web of filaments and voids we observe is a direct consequence of the race between gravitational attraction trying to pull matter together and the finite speed at which gravity propagates. Let's delve into one of the most mind-bending aspects of the cosmic speed limit, the relativity of simultaneity. Imagine two supernovae exploding in different galaxies. For an observer on Earth, they might appear simultaneous, but for someone traveling at high speed relative to Earth, one explosion would clearly happen before the other. There's no absolute answer to which happened first. The order of events depends on your reference frame. This isn't just a measurement problem, it's a fundamental feature of space-time. The universe doesn't have a master clock. Instead, every observer carries their own time, and the speed of light is what relates these different times to each other. The technological implications of the cosmic speed limit shape our modern world in ways most people never realize. GPS satellites must account for both special and general relativistic effects, time dilation from their orbital speed, and gravitational time dilation from being higher in Earth's gravitational field. Without corrections for these effects, GPS positions would drift by about 10 kilometers per day. Your ability to navigate with your phone depends directly on our understanding of how the cosmic speed limit affects time. Particle accelerators have become our primary tools for exploring what happens near the cosmic speed limit. The relativistic Heavy Ion Collider at Brookhaven National Laboratory accelerates gold nuclei to 99.995% of light speed. When these nuclei collide, they create a quark-gluon plasma, a state of matter that existed in the first microseconds after the Big Bang. The extreme energies achieved by approaching light speed allow us to study conditions that haven't existed naturally in the universe for nearly 14 billion years. But there's a puzzle that emerges from quantum field theory. Why is the speed of light what it is? The value, 299,792.458 kilometers per second, seems arbitrary. Why not 300,000 exactly, or twice as fast? Some physicists propose that our universe might be one of many in a multiverse, each with different fundamental constants, including different speed limits. We observe this particular value because it's compatible with the existence of observers like us. In universes with radically different light speeds, stars might not form, or atoms might not be stable, or chemistry might not allow for complex structures like DNA. The search for variations in the cosmic speed limit has led to some of the most precise measurements in science. Astronomers have studied the light from distant quasars as it passes through ancient gas clouds. By analyzing absorption lines in these spectra, they can test whether the fine structure constant, which depends on light speed, has changed over cosmic time. The current limits are extraordinary. If the speed of light has changed at all over the past 10 billion years, it's by less than 1 part in a million. Quantum entanglement continues to challenge our understanding of the cosmic speed limit. Recent experiments have demonstrated entanglement between photons separated by over 1,200 kilometers, with correlations appearing instantaneously. Yet despite this spooky action at a distance, no usable information travels faster than light. It's as if the universe maintains perfect correlations across any distance while still protecting causality. Some physicists interpret this as evidence that space-time itself might emerge from more fundamental quantum entanglements, with the speed of light being a consequence of how information can flow through these quantum networks. The cosmic speed limit affects how we search for extraterrestrial intelligence. Radio signals from a civilization just 1,000 light-years away, practically next door in galactic terms, would take a millennium to reach us. If we detected such a signal and sent a reply, the round-trip conversation time would be 2,000 years. Entire civilizations could rise and fall in the time it takes to exchange a single message. The speed of light doesn't just limit our ability to explore space, it isolates intelligent species from each other, creating lonely islands of consciousness in the vast cosmic ocean. Black holes provide natural laboratories for studying extreme violations of our everyday experience with the speed limit. At the event horizon, space flows inward at the speed of light. Inside the horizon, space flows faster than light toward the singularity, which is why nothing can escape. You'd need to travel faster than light just to stay still. This isn't a violation of relativity because it's space itself moving, not objects moving through space. It's another example of how the universe can create conditions that seem to violate its own rules while actually respecting them at a deeper level. The intersection of quantum mechanics and the cosmic speed limit reveals some of the deepest mysteries in physics. In quantum field theory, virtual particles constantly pop into existence and annihilate, borrowing energy from the vacuum for times so brief they don't violate the uncertainty principle. These virtual particles can technically travel faster than light, but only for distances and times so small that no information can be transmitted. It's as if the universe allows tiny violations of its speed limit as long as they average out to zero and preserve causality on any measurable scale. The cosmic speed limit fundamentally shapes how energy and matter interact throughout the universe. When electrons in atoms jump between energy levels, they emit or absorb photons that must travel at light speed. This creates a minimum time for atomic transitions, which in turn determines the rates of chemical reactions. The speed of light is thus encoded into every biological process in your body, from the firing of neurons in your brain to the molecular machines that copy your DNA. If light speed were different, the chemistry of life would operate on entirely different timescales, potentially making complex organisms impossible. Recent discoveries about neutron star mergers have provided stunning confirmation of the cosmic speed limit's universality. In August 2017, the LIGO and Virgo gravitational wave detectors observed waves from two colliding neutron stars 130 million light-years away. Telescopes around the world then detected light from the same event. The gravitational waves and electromagnetic radiation arrived within seconds of each other after traveling for 130 million years. This incredible precision, matching to better than 1 part in a quadrillion, confirms that gravity and light respect the same cosmic speed limit across vast distances and extreme conditions. The speed of light creates what cosmologists call the particle horizon, the maximum distance from which light has had time to reach us since the Big Bang. This horizon defines our observable universe, currently extending about 46 billion light-years in every direction, more than the 13.8 billion years times light speed due to cosmic expansion. Beyond this horizon lie regions of space we can never observe, no matter how powerful our telescopes become. There could be entirely different structures, different physical conditions, even different laws of physics, but they are forever hidden from us by the cosmic speed limit. Let's explore how the speed of light connects to the nature of mass itself. Einstein's famous equation E equals mc squared tells us that mass and energy are interchangeable, with the speed of light squared as the conversion factor. This isn't just a mathematical relationship, it reveals that mass is essentially energy confined by the cosmic speed limit. The protons and neutrons in atomic nuclei are mostly empty space filled with quarks and gluons zipping around at near light speed. Their kinetic energy, trapped by the strong force, accounts for 99% of the mass of ordinary matter. You are literally made of energy constrained by the cosmic speed limit. The development of laser technology has allowed us to explore what happens when we try to push the boundaries of light itself. In ultra-intense laser fields, the vacuum of space begins to break down, creating electron-positron pairs from pure energy. This vacuum breakdown occurs when the electric field becomes so strong that it can accelerate virtual particles to near light speed before they annihilate, making them real. We're literally ripping particles out of empty space by creating conditions where the cosmic speed limit forces virtual particles to become real. The cosmic speed limit also determines the maximum frequency of electromagnetic radiation. As wavelengths get shorter and frequencies higher, we progress from radio waves through visible light to gamma rays. But there's a limit, the Planck frequency of about 10 to the 43 Hz, where a photon would have so much energy that it would collapse into a black hole. The universe seems to have a maximum clock speed, a fundamental tick rate beyond which even light cannot oscillate. Consider how the finite speed of light affects our perception of reality. When you look at your hand, you're seeing it as it was about 1 nanosecond ago, the time it takes light to travel from your hand to your eyes. When you look at the moon, you see it as it was 1.3 seconds ago. The sun appears as it was 8 minutes ago. We never see the universe as it is. Now, we see a patchwork of different times with more distant objects showing us increasingly ancient history. Reality itself is a kind of time machine, with the present moment being a unique construction of each observer based on their location in space-time. The search for exotic matter with unusual relationships to the cosmic speed limit has led physicists to propose strange possibilities. Hypothetical particles called tachyons would always travel faster than light, experiencing time backward from our perspective. While never observed, the mathematics of such particles isn't forbidden by relativity. They simply couldn't slow down to light speed any more than we can speed up to it. Other proposals include particles with imaginary mass or negative energy, which might allow for exotic phenomena like stable wormholes or warp drives that circumvent the speed limit by warping space-time itself. Modern cosmology has revealed that the cosmic speed limit might be connected to the ultimate fate of the universe. As dark energy accelerates cosmic expansion, distant galaxies are receding from us ever faster. Eventually, they will cross a cosmological event horizon beyond which their light can never reach us, no matter how long we wait. The observable universe is actually shrinking in terms of the number of galaxies we can see. In the far future, the cosmic speed limit will isolate every galaxy cluster in its own observable universe, unable to see or communicate with any others. the role of the cosmic speed limit in quantum computing and information theory has opened new frontiers in our understanding. Quantum information cannot be copied, the no-cloning theorem, or destroyed, and it cannot be transmitted faster than light. These restrictions shape the fundamental limits of computation and communication. As we develop quantum technologies, we're discovering that the cosmic speed limit doesn't just restrict how fast we can travel, it determines the maximum rate at which any computation can process information or any communication system can transmit data. The cosmic speed limit profoundly influences the evolution of the universe on the largest scales. When we observe the cosmic microwave background radiation, the afterglow of the Big Bang, we see tiny temperature fluctuations that represent density variations in the early universe. These fluctuations could only grow into today's galaxies and galaxy clusters because gravity propagates at light speed. If gravity traveled instantaneously, the early universe might have either completely smoothed out or collapsed into black holes immediately. The finite speed of gravitational interaction created a cosmic dance where regions could collapse locally while the universe as a whole expanded, enabling the rich structure we see today. Recent observations from the Dark Energy Survey have revealed how the cosmic speed limit shapes the growth of the largest structures in the universe. Galaxy clusters, containing thousands of galaxies bound by gravity, can only grow so large before the cosmic speed limit prevents their outer regions from knowing about their inner regions quickly enough to maintain stability. The largest gravitationally bound structures we observe, galaxy clusters spanning about 10 million light-years, represent a fundamental limit imposed by the speed of light. Any larger and different parts couldn't coordinate their motion through gravity quickly enough to stay bound together. The interplay between quantum mechanics and the cosmic speed limit creates some of the strangest phenomena in physics. In quantum tunneling, particles can appear to cross barriers instantaneously, seemingly violating the speed limit. However, careful experiments have shown that while the tunneling process itself might be instantaneous, information still cannot be transmitted faster than light. It's as if the universe has multiple sets of books, one for particles and another for information, and while particles might occasionally bend the rules, information transfer remains strictly limited by light speed. Let's explore how the cosmic speed limit affects the most extreme objects in the universe. Magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's, can accelerate particles to near light speed within microseconds. The magnetic fields are so intense that they polarize the quantum vacuum itself, creating a birefringent effect where light of different polarizations travels at slightly different speeds. Yet, even in these extreme conditions, the average speed of light remains constant, demonstrating the robustness of the cosmic speed limit even in the most violent environments nature can create. The study of gamma-ray bursts, the most energetic explosions in the universe since the Big Bang, has provided remarkable tests of the cosmic speed limit. These explosions, lasting from milliseconds to minutes, can briefly outshine entire galaxies. The gamma rays from bursts billions of light-years away arrive at Earth with different energies within fractions of a second of each other. If higher energy photons traveled even slightly faster or slower than lower energy ones, they would arrive separated by years or centuries. The simultaneous arrival confirms that all light, regardless of energy, respects the same cosmic speed limit across billions of light-years of intergalactic space. The cosmic speed limit creates fundamental limitations on our ability to map the universe. As we look deeper into space, we see objects as they were in the past, but we can never know their current state. Distant galaxies we observe might have already collided, exploded, or transformed in ways we won't see for billions of years. This creates a profound epistemological limit. We can never have complete knowledge of the universe's present state. Our maps of the cosmos are always maps of the past, with more distant regions showing increasingly ancient history. The development of atomic clocks has allowed us to measure the effects of the cosmic speed limit with extraordinary precision. Optical lattice clocks can now measure time so accurately that they can detect the gravitational time dilation from raising the clock by just 1 centimeter. These clocks have confirmed that time really does slow down in gravitational fields and for moving objects, exactly as Einstein predicted. The cosmic speed limit isn't just a theoretical concept, its effects are measurable in laboratory conditions here on Earth. Consider how the cosmic speed limit affects the search for dark matter. If dark matter particles interact with ordinary matter only through gravity, then any changes in dark matter distribution can only affect us at light speed. This means dark matter halos around galaxies must be stable over billions of years. Any faster changes would have torn galaxies apart. The cosmic speed limit thus constrains the properties of dark matter, helping physicists narrow down what this mysterious substance might be. The finite speed of light also plays a crucial role in the stability of atoms themselves. Electrons orbiting atomic nuclei are already moving at significant fractions of light speed. In heavy atoms like gold and uranium, inner electrons reach speeds of over half light speed. This relativistic motion affects their orbital characteristics, contributing to gold's yellow color and Mercury's liquid state at room temperature. If the cosmic speed limit were different, the periodic table would be reorganized, with different elements being stable and having different properties. Recent advances in laser wake-field acceleration have pushed electrons to energies where they experience time dilation factors of thousands. In these experiments, electrons are accelerated to 99.999% of light speed over distances of just centimeters. From the electron's perspective, the laboratory appears contracted to the size of a human hair. These experiments are providing new insights into how matter behaves at the extreme edge of the cosmic speed limit, and might eventually lead to new technologies for medical imaging and particle physics research. The cosmic speed limit even affects how we might communicate with potential extraterrestrial civilizations. The breakthrough. Listen Project, scanning millions of stars for signs of intelligent life, must contend with the fact that any signals we detect would be years or centuries old. If we detected a signal from a civilization 500 light-years away and sent a response, the round-trip communication time would be 1,000 years. Entire civilizations could rise and fall between messages. The cosmic speed limit doesn't just make interstellar travel difficult, it makes interstellar conversation nearly impossible on human timescales. The relationship between the cosmic speed limit and the fundamental forces of nature reveals deep connections in the architecture of reality. The electromagnetic force, carried by photons traveling at light speed, can reach across infinite distances, though its strength diminishes with distance. The strong nuclear force, which binds quarks into protons and neutrons, is carried by gluons that also travel at light speed, but the peculiar nature of the strong force confines them to subatomic distances. The weak nuclear force, responsible for radioactive decay, is mediated by W and Z bosons that are massive and thus travel slower than light, limiting their range to subatomic scales. This hierarchy of forces, all respecting the cosmic speed limit in their own ways, creates the rich complexity of matter we observe. Recent discoveries in condensed matter physics have revealed that the cosmic speed limit manifests in unexpected ways in material systems. In certain materials called photonic crystals, scientists can slow light down to walking speeds or even bring it to a complete stop. In Bose-Einstein condensates, ultra-cold gases near absolute zero, researchers have slowed light to just 17 meters per second. Yet this isn't violating the cosmic speed limit. The photons still travel at c between atoms. but their constant absorption and re-emission by the atoms creates an effective slower speed. It's like a car traveling at highway speeds, but making so many stops that its average speed is much lower. The cosmic speed limit plays a crucial role in the phenomenon of Hawking radiation from black holes. According to quantum mechanics and general relativity, black holes slowly evaporate by emitting radiation. This process is incredibly slow for stellar mass black holes. A black hole with the mass of our Sun would take 10 to the 67 years to evaporate completely. The temperature of this radiation is inversely proportional to the black hole's mass, and the radiation must respect the cosmic speed limit as it escapes from just outside the event horizon. This creates a profound connection between the cosmic speed limit, quantum mechanics, and thermodynamics. Let's explore how the finite speed of light affects our understanding of cosmic inflation, the period of exponential expansion in the universe's first fraction of a second. During inflation, space itself expanded faster than light, which might seem like a violation of the cosmic speed limit. However, this is perfectly allowed by general relativity because it's space itself expanding, not objects moving through space. This distinction is crucial. The cosmic speed limit restricts motion through space, not the expansion of space itself. Inflation could separate regions that were initially in causal contact, explaining why the universe looks so uniform despite regions that could never have communicated at light speed. The cosmic speed limit creates what physicists call horizons throughout the universe. Beyond the cosmic event horizon, about 16 billion light-years away, galaxies are receding so fast due to cosmic expansion that their light will never reach us. Inside black holes, the event horizon marks where space flows inward faster than light can travel outward. In accelerating reference frames, Rindler horizons appear, beyond which events cannot influence the accelerating observer. These horizons aren't physical barriers but boundaries in spacetime, created by the finite speed of information propagation. Modern experiments with ultra-intense lasers are probing what happens when electromagnetic fields approach the limits imposed by the cosmic speed limit. The Schwinger limit, about 10 to the 18 volts per meter, represents the electric field strength at which the vacuum itself breaks down, spontaneously creating particle-antiparticle pairs. Current lasers can achieve fields about 1 million times weaker than this limit, but future facilities might approach it. At these intensities, the vacuum becomes a nonlinear medium, and our usual understanding of light propagation breaks down. The cosmic speed limit remains inviolate, but the behavior of light and matter enters uncharted territory. The search for quantum gravity, a theory unifying general relativity and quantum mechanics, is intimately connected to understanding the cosmic speed limit at the smallest scales. Some theories suggest that at the Planck length, about 10 to the minus 35 meters, space-time itself becomes quantized. Light traveling through this quantum foam might experience tiny variations in speed, accumulating over cosmic distances. Observations of gamma rays from distant cosmic explosions have placed stringent limits on such effects. If space-time is quantized, it's smoothed to at least 1 part in 10 to the 17. Consider how the cosmic speed limit affects the concept of cosmic censorship, the hypothesis that singularities are always hidden behind event horizons. When matter collapses to form a black hole, the formation of the event horizon is governed by the speed of light. The horizon forms and expands outward at light speed, racing to enclose the forming singularity before any information about the singularity's bizarre physics can escape. It's as if the universe uses its speed limit to hide its most extreme secrets from outside observers. The role of the cosmic speed limit in determining the universe's information content is profound. The holographic principle suggests that the maximum information content of any region is proportional to its surface area, not its volume. This surprising result emerges because information must be accessible to outside observers, and the cosmic speed limit restricts how much information can be read from a region's interior in finite time. A sphere 1 meter across can contain at most about 10 to the 70 bits of information, any more, and it would collapse into a black hole, hiding the excess information behind an event horizon. Recent observations of fast radio bursts, mysterious millisecond pulses of radio waves from distant galaxies, have provided new tests of the cosmic speed limit across different wavelengths. These bursts travel billions of light-years through the intergalactic medium, yet their different frequency components arrive within milliseconds of each other. This places stringent limits on any variation of light speed with frequency. If such variations exist, they're smaller than 1 part in 10 to the 15. The universe's speed limit appears to be truly universal, independent of the energy or wavelength of electromagnetic radiation. The cosmic speed limit fundamentally shapes how complexity can arise and evolve in the universe. Chemical reactions, biological processes, and even thoughts in your brain are all rate-limited by how fast electromagnetic forces can propagate between atoms and molecules. If light speed were significantly different, the timescales for these processes would change dramatically. A faster light speed might make chemical reactions too quick for complex molecules to remain stable. A slower light speed might make biological processes too slow for evolution to produce complex life within the age of the universe. We exist in a cosmic sweet spot where the speed limit allows for both stability and change on timescales conducive to life. The implications of the cosmic speed limit for the ultimate fate of the universe are both profound and sobering. As dark energy continues to accelerate cosmic expansion, we're approaching what cosmologists call the de Sitter horizon, a future state where every galaxy cluster will be isolated in its own observable universe, surrounded by an event horizon beyond which nothing can ever be seen. The cosmic speed limit, combined with accelerating expansion, will eventually create countless island universes, each forever alone, unable to see or communicate with any others. In about 100 billion years, future astronomers in our galaxy will see only darkness beyond our local group, with no evidence that other galaxies ever existed. The study of time crystals, structures that repeat in time rather than space, has revealed new ways that matter can organize itself while respecting the cosmic speed limit. These exotic states of matter, first created in 2016, oscillate at their own frequency without consuming energy, seeming to violate thermodynamics. However, they still respect causality and cannot transmit information faster than light. They represent a new phase of matter that exists only because of the interplay between quantum mechanics and the cosmic speed limit, showing us that nature still has surprises even within the constraints of known physics. Let's delve into how the cosmic speed limit affects the possibility of time travel. While general relativity allows for closed, time-like curves, paths through space-time that loop back to their own past, every proposed mechanism for creating them requires exotic matter with negative energy density or other conditions that may be physically impossible. The cosmic speed limit seems to protect causality through what Stephen Hawking called the chronology protection conjecture. The universe appears to prevent the formation of time machines that could violate cause and effect. Quantum effects near any would-be time machine would likely destroy it before it could operate. Recent advances in metamaterials have created substances with extraordinary optical properties, including negative refractive indices that make light appear to travel backward. Some researchers have even proposed space-time cloaks that could hide events by manipulating the speed of light in materials. Yet all these effects work by controlling how light propagates through matter, not by violating the fundamental cosmic speed limit. They're like creating traffic patterns that seem to violate traffic laws while actually following them perfectly, clever arrangements that create illusions while respecting the underlying rules. The cosmic speed limit determines the maximum rate of quantum entanglement generation in the universe. While entangled particles exhibit instantaneous correlations regardless of distance, creating new entanglement requires bringing particles together or having them interact through forces that propagate at light speed or slower. This means the universe's total entanglement is constantly increasing, but at a rate limited by c. Some physicists speculate that spacetime itself might emerge from quantum entanglement, with the cosmic speed limit reflecting fundamental constraints on how quantum information can flow and create the classical world we observe. Consider how the finite speed of light affects the growth of cosmic voids, vast regions of space containing very few galaxies. As the universe expands, these voids grow larger, but their growth is limited by how fast gravity can pull matter away from void centers. The largest voids, spanning hundreds of millions of light-years, represent equilibrium between cosmic expansion and the speed at which gravitational information can propagate. The cosmic speed limit thus shapes not just where matter clusters, but also where it's absent, creating the Swiss cheese structure of the cosmic web. The development of gravitational wave astronomy has opened an entirely new window for testing the cosmic speed limit. Every detection confirms that gravitational waves travel at exactly the speed of light, as Einstein predicted. But these observations go further. They show that the speed is the same across billions of light-years and through various cosmic environments. Even as these waves pass through galaxy clusters, dark matter halos, and cosmic voids, their speed remains constant. The universe's speed limit is remarkably robust, unaffected by the matter and energy the waves encounter on their journey. The cosmic speed limit plays a crucial role in the phenomenon of gravitational lensing, where massive objects bend the path of light from distant sources. Because light travels at finite speed and takes the path of least time through curved spacetime, we can see multiple images of the same distant galaxy or quasar, each image showing the object at a different time in its history. In some cases, we've observed the same supernova explosion multiple times, months or years apart, as its light took different paths around an intervening galaxy cluster. The cosmic speed limit turns massive objects into time delay lenses, allowing us to watch cosmic events in replay. Modern proposals for interstellar travel must all grapple with the cosmic speed limit, from fusion rockets to antimatter engines to solar sails pushed by powerful lasers. Every concept faces the same fundamental barrier. Even the most optimistic proposals typically achieve only a few % of light speed, meaning journeys to nearby stars would take decades or centuries. Some physicists have proposed more exotic solutions like Alcubierre drives that would warp spacetime to move a bubble of space faster than light, but these require exotic matter that may not exist and energies equivalent to converting entire planets to pure energy. The relationship between the cosmic speed limit and consciousness raises profound questions about the nature of mind and reality. Neural signals in your brain propagate at speeds far below light speed, typically tens of meters per second. Yet the electromagnetic fields generated by neural activity propagate at light speed. Some theories of consciousness propose that these fields play a crucial role in binding disparate neural processes into unified conscious experience. The cosmic speed limit might thus be fundamental to consciousness itself, determining the maximum rate at which different parts of the brain can be integrated into a single experiencing subject. As we push the boundaries of technology and observation, we continue to find new ways that the cosmic speed limit shapes reality. From the smallest subatomic particles to the largest cosmic structures, from the beginning of time to the far future, this universal constant weaves through every aspect of existence. It's not just a speed limit, it's the fundamental rate at which cause and effect propagate through the universe, the maximum speed of information transfer, and possibly the key to understanding why the universe exists at all. As we reach the culmination of our journey through the cosmic speed limit, it's time to step back and appreciate the profound unity this universal constant brings to our understanding of reality. The speed of light isn't just a number, it's the fundamental heartbeat of the universe, the rate at which existence itself unfolds. From the quantum foam at the Planck scale to the cosmic web, spanning billions of light years, from the first moment of the Big Bang to the ultimate fate of the cosmos, this single constant ties everything together in an elegant tapestry of cause and effect. The most recent breakthrough in our understanding came from the detection of gravitational waves from colliding neutron stars, which produced both gravitational and electromagnetic signals. After traveling 130 million light-years, these fundamentally different phenomena, ripples in space-time itself and electromagnetic radiation, arrived within seconds of each other. This observation confirmed to extraordinary precision that gravity and light respect the same cosmic speed limit. It's a beautiful vindication of Einstein's vision that all of physics, from the quantum to the cosmic scale, operates within the same relativistic framework. But perhaps the deepest insight is that the cosmic speed limit makes our existence possible. If light traveled infinitely fast, causality would be instantaneous everywhere, potentially creating paradoxes that would make a stable universe impossible. If it traveled much slower, stars couldn't shine efficiently, chemistry would operate on timescales incompatible with life, and the universe might have recollapsed before complexity could arise. The specific value of c appears fine-tuned for a universe capable of producing observers who can contemplate their own existence. This brings us to one of the most profound questions in physics. Is the speed of light truly fundamental, or does it emerge from something deeper? Some theories suggest that space-time itself might be emergent, arising from more fundamental quantum structures. In loop quantum gravity, space consists of discrete loops at the Planck scale. In string theory, vibrating strings in higher dimensions give rise to the particles and forces we observe. In these frameworks, the speed of light might be a derived quantity, emerging from the dynamics of these more fundamental entities. Recent observations continue to push the boundaries of our understanding. The Event Horizon Telescope, which gave us the first image of a black hole's shadow, is now working to create movies of matter swirling around black holes at near light speed. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will detect gravitational waves from supermassive black hole mergers, testing the cosmic speed limit in the most extreme gravitational fields in the universe. The proposed Einstein telescope will be sensitive enough to detect quantum fluctuations in space-time itself, potentially revealing whether the speed of light has quantum uncertainties at the smallest scales. The philosophical implications of the cosmic speed limit extend beyond physics into questions of meaning and purpose. In a universe without this limit, every point would be instantly connected to every other point. There would be no room for independence, growth, or genuine novelty. The cosmic speed limit creates pockets of autonomy throughout the universe, regions that can evolve independently, at least temporarily, from the rest of the cosmos. This might be essential for the emergence of complexity, life, and consciousness. The universe's speed limit doesn't constrain us, it liberates us, creating the space for genuine creativity and evolution. As we look to the future, the cosmic speed limit will continue to shape humanity's destiny. Whether we remain on Earth or spread throughout the galaxy, we'll always be constrained by this fundamental constant. Interstellar civilizations, if they exist, must be patient civilizations, adapted to the vast timescales imposed by the cosmic speed limit. Perhaps this is why we haven't detected signs of alien intelligence, not because it doesn't exist, but because the universe's speed limit naturally isolates civilizations, making contact rare and precious when it occurs. The cosmic speed limit also carries a message of humility. Despite our technological prowess, despite our scientific understanding, we remain bound by the same laws that govern stars and galaxies. We cannot outrun light, cannot send messages into the past, cannot escape the forward flow of time. Yet within these constraints, we've achieved remarkable things. We've detected gravitational waves from colliding black holes, billions of light years away. We've measured time dilation with clocks accurate to 1 part in 10 to the 18. We've pushed particles to 99.99999% of light speed. We've turned the universe's fundamental limit into a tool for understanding the cosmos itself. In the end, the cosmic speed limit reminds us that we are part of the universe, not separate from it. The same constant that governs light from distant galaxies governs the chemical reactions in our cells. We are patterns of matter and energy that have temporarily organized themselves to contemplate the very laws that make our existence possible. Every thought you think, every heartbeat, every breath operates within the framework established by the cosmic speed limit. So the next time you look up at the stars, remember that their light has traveled for years, centuries, or millennia to reach your eyes, all at the same cosmic speed limit that governs everything in existence. You're not just observing the universe, you're participating in it, connected to the most distant galaxies by the universal constant that makes physics possible. The cosmic speed limit isn't a barrier, it's the foundation that allows the universe to exist, evolve, and eventually know itself through conscious beings like us. This is the profound gift of understanding why the universe has a speed limit. It's not an arbitrary restriction, but a fundamental feature that makes possible the rich, complex, evolving cosmos we inhabit. From the quantum to the cosmic, from the beginning of time to the far future, the speed of light weaves through reality, binding everything together while allowing genuine novelty to emerge. We are children of this cosmic speed limit, and in understanding it, we understand something essential about ourselves and our place in the grand story of existence. If you made this far, make sure to subscribe and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. What would really happen if you traveled at light speed? If you're fascinated by the speed of light, interstellar travel, and the mysteries of space-time, this is the ultimate guide to what really happens at light speed. See you there.